Hello, this is Mr. McMurray. Welcome to Chapter 9. Hopefully you've all survived exam number 2, or if you haven't taken that yet, we'll shortly. Um, we are at the halfway point. I believe most people still need to turn in their article summaries, so don't forget to do those if you haven't done those. All right, but like I said, things are heating up because we are talking about thermal energy or heat this week. Okay, lots of stuff to cover, so let's just hopefully some cool demonstrations. So let's just get with it. All right, heat is one of those things you can't see. It's something you feel. It's a form of energy, and kinetic energies. It's kind of hard to put your finger on exactly what it is sometimes. Okay, we all know what it is when we feel it, but it's hard to explain heat sometimes. Or what exactly is it? People thought at least it used to be a substance that was in some things. Things that would burn obviously had, they call it phlogiston, okay? And they even have a symbol for it in the alchemy circles, okay? And said this is phlogiston. It's this element. If something contains phlogiston, then you burn it, it gives off heat, and there you go. And the more phlogiston it has, the more you can do that. Things like rocks that don't burn obviously don't have much phlogiston in them. Other things like wood, for example, and so forth, paper, whatever, they obviously have phlogiston in them. And it's not totally completely wrong. There's something in them, and they have to be exposed to oxygen. But the idea was that heat was some kind of substance that, like an element that got taken into certain things and then released. Okay. Then they got rid of the idea of phlogiston. They talked about the caloric. Okay, and caloric was something that got into things and so forth. But at any rate, uh, um, an important theory was eventually put forth, which is called the kinetic theory of matter. And basically, the idea is that heat is related to motion. Okay, kinetic. Okay, obviously moving, things are moving, and basically matter is in different phases, solid, liquid, gas, depending on how much heat there is, and that as you add heat to it, the atoms move faster. So you have a solid where the atoms are tightly packed together. They can't move very much. That's why they're solid. Okay, and so all they can do is kind of vibrate in place. But if you heat them up, they vibrate faster and faster and faster. Eventually, they're going to break loose enough that they can start sliding around. And now we have a liquid, okay? And so in the liquid, they can move around inside the liquid, but they can't just go popping off out of the liquid unless you get them hot enough, and then the atoms that are in the liquid will actually break loose. And now they're just bouncing around all over the place in the air, okay? The space around them. And so that is a gas, okay? And that's basically the kinetic theory of matter, is that all atoms are have atoms, all atoms and all substances are moving at least at some point. The least in a solid, and then more in a liquid, and the most in gases bouncing around. Okay, and so we know if you go from a solid to a liquid, say it's a piece of ice, it melts, it turns into water. Okay, so that's melting. Okay, if we go from a liquid to a gas, that can either be evaporation or boiling. Okay, I think we'll go over that in the other lecture, so I'm not going to spend a lot of time on that. Evaporation happens at lower temperatures, and it's only some of the molecules in the liquid get enough energy and leave, and so it takes a long period of time for that to happen. Boiling is when the whole temperature reaches a certain boiling point, and all the molecules can start becoming gases all at once. All right, but those are a little bit different, but they're both going from a liquid to a gas. Okay, now you can also go the opposite direction. You can go from a gas back to a liquid, which is condensation. Dew in the morning, as it gets cold at night, it can't hold as much moisture in the air, so some of it changes from a gas back to a liquid. If I have a glass of ice water, which I do over here, but I can't get it right now, it cools the water vapor in the air enough that all of a sudden you get the sweat or condensation on the outside, and then leaks down, runs your mom's table, and she yells at you and screams. At least that's how it worked at our house. Anyhow, but that's condensation. You can go from a liquid back to a solid, which we usually talk about as freezing, but technically solidification might be a better word, just because most of the time when we talk about freezing, we say it's freezing outside. Well, technically, everything in this room, well, most of the things in this room are frozen. Okay, the plastic in this chair over here, all right, it's frozen. The metal in the legs are frozen. Why? Because they're solid. So we don't really say they're frozen, but they are. They're below their freezing point, and therefore they are solids. If we heat both those up, the plastic would melt first, and then eventually the metal would melt also, okay, and become a liquid. So The freezing point we're usually talking about is for water because we're living things, we're made out of water, water's everywhere, so we use that as our reference point to freezing. But technically, every substance has its own freezing, melting point, boiling point, and so forth. Okay, so keep that in mind. All right, so we call solid solidification sometimes to confuse that. Now, you can go straight from a solid straight to a gas, okay, and that's called sublimation. If you have dry ice, what they do is they take carbon dioxide, they get it, put so much pressure and get it cool and cool it down, and it cools down so much that it turns into a solid. So basically, they've taken a gas, CO2, and gone straight to a solid. Okay, well, when they take that out, then it goes the other direction. It goes sublimes back into a gas, and actually, what happens is it cools the air so much the water vapor turns back into water droplets, and so it literally makes a fog. Okay, a lot of times people say, "Oh, that's the carbon dioxide gas," but you can't see carbon dioxide gas. But it's so cold it cools the air that it's mixing with, and it causes the water droplets to actually form and make a fog. All right, that's sublimation. Now, the other direction we don't hear much about. That's where you go from a gas to a solid. Okay, and that's called deposition. In fact, the first time we talked about heat in physics, I had to look up that word because no one really talks about that ever, but it happens all the time. In your freezer, for example, if you have a frost-free freezer, it'll kind of take care of this for you. But in the older freezers, and still a lot of the freezers today, water vapor in the air changes directly to ice crystals, and you get the frost in your freezer. In a gallon of ice cream, should it last long enough in the refrigerator, okay, the water that's in the ice cream changes to water vapor, freezes, and it doesn't change to water vapor. It changes straight to water vapor. It doesn't melt. You can't melt in the freezer, right? But it changes directly to water vapor, and then the water vapor freezes and goes straight to a solid, makes ice crystals. And so if you look on the inside of the ice cream container, if it's been in there long enough, there'll be ice crystals on the top. Also, the ice cream will be kind of yucky. Why? Because it's losing moisture. It's kind of drying out, basically. And so it doesn't taste as good. Why? Because it's lost some of the moisture that used to be in it, the water that used to be in it. Okay? This happens all the time in the wintertime. In the mornings, you're scraping deposition off your windshield. Why? Because it's not ice, it's water vapor that changed directly into ice crystals or frost. Okay? It also happens. My brain just went dead. Sorry. Yeah, don't worry about it. Okay, but frost is a very common example of deposition. That's going from a gas straight to a solid. All right. Okay. Enough about that. Let's move on and do some things that we can do some experiments about. We're not going to talk about plasma. I'm going to talk about that in the other lecture. Okay, so let's move on for a little bit. All right. Temperature then has to do, when we measure temperature, it has to do with heat. Okay, but it's not the same as heat. We'll talk about what heat is versus temperature in a minute. But temperature is how fast are the atoms moving. Okay, so when we talk about the temperature of something, we're really talking about how fast are the atoms moving in it. Okay, all right. Now, we've talked about this before. We're going to do it again. If you look at this, it looks like a light bulb, except for instead of a light fixture inside, it just has a bunch of little flags on the middle here. And some of them are black on one side. They're all black on one side, white on the other side. You see if they spin around there, they change from dark to light. Okay, some of the air has been sucked out of this, so it's a partial vacuum. That way there's not much air resistance. Okay, and this thing is sitting on top of a pin. It just kind of bounces in there, so it doesn't take much to spin it. There's very little friction because just the little tip of the pin's touching it. All right, now, so what we're going to do is, notice if I blow on it, it doesn't do anything. Why? Because it's not impressed by that. Okay, it's completely sealed and whatever, and I can't touch it. But if I put a light on it like so, we will notice that it starts to spin faster and faster and faster. Okay, so I'm going to take the light away just so you can see it's actually spinning pretty fast right in there. Okay, and get that. Now, we could go and try to prove this is not just a matter of having light. It could be light energy, but we will just go ahead and discuss this. And this is actually causing it to spin is because of heat energy. Okay, it's not the light. When the light hits the dark side, it absorbs the heat. It heats up. Air molecules that are next to it heat up, okay, by conduction, touching it. We'll talk about that later. Okay, as they heat up, they start moving faster. When things get hot, they move faster. They move faster and faster. That means they hit with more momentum, okay? And therefore, they're going to push harder on the side with the hot molecules than the white side of the flag where it's not as hot. It did not absorb as much heat, and so the molecules aren't moving as fast. And since there's a greater force on the black side, it causes it to spin in that direction, okay? Starting to slow down a little bit now, and eventually it will stop if we let it go there. It will always spin the same direction. Why? Because it's the molecules hitting on the black side and pushing it around the other direction. All right, but heat causes things to move faster. If there's less heat, then they'll move slower. Notice I didn't say cold if they're colder. Cold is not a thing, okay? Cold doesn't move into things. We go outside and say, oh, the cold got into my body. It's like, no, the heat left your body. Cold is the absence of heat. So if you got cold, that's because heat leaving your body, okay? All right, so basically, talking about temperature, we measure temperature in degrees Fahrenheit or degrees Celsius or Kelvin, all right? And basically, since temperature is how fast they move, there is no limit. I guess the speed of sound technically might be a limit, but we've never got anything that hot. Hottest thing we know is near some stars, but basically, if it gets hotter and hotter, if they move faster and faster, there's really no limit on temperature, okay? But there is a limit on how cold things can get or how much heat they can lose, because if heat is how fast the molecules are moving, then the coldest they can get is when there's no movement at all, okay? And that is what we call absolute zero. Now, I'm not going to go into all that because it's in the other lecture, I think, but absolute zero is 0 Kelvin, not 0 degrees Kelvin, just 0 Kelvin. That's the unit they use for that. And basically, that's the temperature at which all motion stops, and therefore there is no heat present. Okay, cold, in this case absolute zero, the coldest that you can get is the absolute absence of heat, and therefore the absence of motion in the atoms. All right, now let's talk about the ideas of heat versus thermal energy. Okay, thermal energy first. Okay, let's say that I have a bottle here, and in my cup, Arctic cup actually, it is full of hot coffee. Okay, and outside we have a swimming pool. Question is, which one has the most thermal energy? Well, if I stick my finger in the boiling hot coffee, it will hurt. And no, it doesn't mean I can sue whoever made the coffee. Okay, but it's hot and it will burn me. But obviously, if I stick my hand in the swimming pool, it's air temperature, which right now is only about 80 degrees. It's not going to hurt. So he said, oh, this has more thermal energy. And if we're talking about, I guess, density, it's packed. The thermal energy in this is packed into a small amount. It would be right, but that's not correct. Why? Because it depends on two things. One, it depends on the kinetic energy or the temperature of it. And this one does have a higher temperature, but it also depends on the mass of it. Okay? This is a relatively small mass. Okay, 20 ounces, 30 ounces, I forget, but I forget what that is in milliliters, but let's say less than a liter. Okay, about a liter is all this is. The swimming pool, on the other hand, is thousands of gallons. There's a lot of it, and even though the temperature, kinetic energy of each molecule is less than the temperature averaged molecule kinetic energy of the molecules in here, it has a lower temperature. Overall, there's so many molecules out in the swimming pool, it's going to have a greater thermal energy. That's why if I take this boiling hot coffee, I pour the coffee out in the swimming pool, if you're sitting in the swimming pool, you probably won't even notice, as in the color, of course, but probably just think some little kids were out there and didn't go to the restroom. Okay, but anyhow, we won't go there. But at any rate, you might see a slight color change, but you will not probably feel any temperature difference. Why? Because by the time this thermal energy in the coffee is spread out through the whole mass of the swimming pool, it's not going to make much difference. Okay. Now, the other thing is, don't think that the swimming pool is empty. Remember, absolute zero is negative 273 degrees below zero. It's really, really cold. Even things that are frozen, like this piece of ice, for example, right here, okay, it still has a lot of thermal energy in it. Why? Because 0 degrees Celsius is 273 degrees above absolute zero. It's still got a lot of thermal energy compared to absolute zero. So just because something feels cold, that doesn't mean it has zero thermal energy. Okay, uh, remember zero is absolute zero, which is negative 273, and nothing has ever gotten that cold. Okay, yet we haven't been able to get things quite that cold. Got close, but never quite got there. Okay. So thermal energy depends on the temperature, kinetic energy of the molecules, but it also depends on the amount of them. Okay, if you have large amounts. Okay, another example in the opposite direction: sparklers have very high temperatures for those little sparks, but by the time they break off and it spreads out into the air around it, there's such a small amount. Those little sparks are so tiny that by the time they spread their heat out, no one feels it. Now, if you were to stick one in your eye and it goes directly in your, yeah, that's going to be a different deal. But in general, they're not going to be harmful. You go, ooh, that spark hit me, I'm going to die or something. Okay, no, because even though it has a high temperature, it's such a small amount of matter that by the time that heat hits something and spreads out, it's not going to be enough to really matter much. Okay. So once again, temperature is the average kinetic energy, or how fast the molecules in the substance are moving. All right. So heat, though, is not the same as temperature. Okay. Heat is when it moves from one object into another object. Okay. When the heat flows from one place to another. All right. So what does that mean? Well, uh, first of all, um, things always move from hotter objects into colder objects. Okay. So let's go back to my ice thing here. All right. I have water in here and I have ice cubes. All right. The temperature, the heat is flowing when I put ice into a drink. Say I have my theoretical coffee here, and I start putting ice cubes in it. Okay, we say, it cools down my drink. Well, what really happens is it acts like a heat magnet. Why? Because it's the coldest thing in the area. So all the heat that's in the liquid rushes into the colder ice. It always goes from high temperature to lower temperature. And so it does that until the temperature is the same. Then it quits flowing and it reaches the temperature, which is right about 0 degrees Celsius or 32 Fahrenheit. It's right about freezing. Okay, so the temperature is right about freezing. But once they get to equal, then it quits flowing. Okay, and it would stay in equilibrium. Now, if it were sealed off from the rest of the world, but guess what? The room is warmer than that, so there's constantly heat from the air. Of course, there's not very many air molecules because they're all spread out, but they're sending heat into this. So eventually, all the ice will melt and the water will warm up to room temperature. Why? Because heat in the room, which is hotter, is going to keep doing that. Now, it gets the air around it cold. That's why you have condensation all over this. Okay, we talked about that. But eventually, it's going to try to equal out. It wants everything to be the same, and so it's always going from hotter into colder. But people go outside and say, "Oh, that cold just ate into me." Well, no, that's the feeling of heat leaving your body. Okay, kind of like what was it? Pain. Oh, that's what it was. Pain, just weakness flowing the body, which I never bought from the coaches. But anyhow, um, that cold you feel is actually the feeling of heat leaving the body, and that is a fact. Okay, and that is good science. Okay, so heat always flows. Now, the bigger the temperature difference, then the faster it will flow. Okay, and so when you go outside on a cold day, then the heat flees your body a lot quicker, and so you get colder quicker because the heat is leaving faster. Okay, if today is 80 degrees outside, yes, there's heat going from my body into the air, which is 80 degrees. That's cooler than my body, but it's fairly slow loss of heat, so I don't really feel that too bad. All right. All right. Now, what do we measure heat? We measure heat in calories. Well, what's a calorie? That's what's in our food, right? Yes, but a calorie, technically by definition, is if you had a cubic centimeter, 1 centimeter by 1 centimeter by 1 centimeter, like this die here. Okay. If you had that much water, this is actually a little bit bigger than that, actually. So it's be a little bit smaller than this. It's the amount of heat energy it takes to make 1 gram or cubic centimeter or milliliter cube of water go up 1 degree Celsius. Now, if I'm just holding this in my hand, it's probably already gone up 4, 5, 6, 7, 8 degrees Celsius. So I'm putting multiple calories into it. Okay. Now, just for the record, when we started measuring food calories, you have a candy bar, it might have 200 and something thousand calories. So they said, hey, we're going to make food calories, or really what we call kilocalories, or thousands of calories. And so instead of being 200 and something thousand, it's just 200 something calories, and they're really thousands of calories. So just keep that in mind, just so you know. All right. Okay, so that's the dye there. Now, let's talk about something else. Specific heat. All right, not just general heat, but specific heat. Well, what does that mean? A specific amount of heat? What are we talking about here? Well, let's just say it. I have this hot plate turned on. Oops, that's the wrong one. Let me turn this one on. Okay. All right, if I turn it on, I feel heat, hence the name hot plate. Okay. But I have two pieces of metal. One is, it's about 58 grams of copper, I believe. Yep, that one is. Kind of been tarnished, so it's not gold anymore. And this one is aluminum. Now, they are the same amount mass-wise. This is 58. This is about 58. The aluminum is a lot bigger. Why? Because it is less dense. That's right. And so there we go. We put these on there. Now, if we put these on here, they're going to absorb the same amount of heat, right? Thermal energy coming from this, it's producing a certain amount, and they're going to absorb about the same amount. Let's put them kind of next to each other in the middle there. All right. Now, we will come back and visit those in a moment. All right. All right. I don't sure if I said all that on camera or not, so we're going to take a little break and let these warm up, and we'll be right back. We're about ready to do this. But before we do that, let's talk about a couple things. One, first of all, how does the thermometer work then? Well, basically, we put a thermometer in something. If it's hotter, the heat goes into the thermometer until it equalizes. It's the same as the temperature of what it's in, whether it's a glass thermometer or a probe like this one. Okay, it doesn't matter. It's basically going to, heat will flow into the colder thermometer if the liquid's hotter until it equalizes. Or if you put in something cold, the heat will flow out of the thermometer until it's the same as its surroundings. So that whole heat flow thing is what makes the thermometer work. All right. So if I put in this liquid, all right, it will have air flowing back and forth until it's about 79 degrees. Okay. This one here is about 77 degrees, slightly different temperatures, but basically about the same thing. Now, what we're going to do is we're going to take these two pieces of metal, and by the way, I've thrown on a Coke can. We'll explain here in a minute, but not to worry about it right now. We still have these two pieces of metal, the aluminum, all right, and the copper. Okay, now we're going to put them, we have water in these two things, okay, and they're a little bit, a couple of degrees off. This is 79.9, this is about 77. They're about the same temperature water. It's also the same amount of water, same mass of water. Remember, both of these two metals have the same mass also, okay? I'm going to take the metal, though, and put it in here. Now, if we put it in here, we know that what's going to happen? Well, the hot, which is going to be the metal, is the heat's going to leave the hot metal and go into the water until they are the same temperature. Now we're putting the same mass of metal into the same mass of water, so we would expect the temperatures to be, probably the same. So let's try that and see. You hear all the sizzling in there. Okay, that's the metal. And then the other one, we will put the copper in. You may have noticed it had a little popper fizzle there, okay? And let's see what happens to the temperatures of these two. Okay, as they go up. Okay, we know we would expect them to be going up because the heat is going from the metal into the water. Okay, and we do that. Now, the question is, were these two pieces of metal the same temperature when we put them in there? Well, the metals were not the same temperature. Now, interestingly enough, they heated the water up the same amount. This one's 93 and this one's 93 because water heats up the same amount. Okay, same amount of thermal heat. But if we had taken the temperature of the metals before, we would have found that the copper metal was actually a whole lot hotter. Okay, why? Because it has what we call a different specific heat. Okay, and a fairly low specific heat. We have done this experiment before, and we've taken the temperature of the water, the copper, and found that it was like 300 or 400 degrees. Okay, so very, very hot. Okay, whereas I have a tin can full of water here, and it's boiling, so it's a little bit over 100 degrees Celsius, but it's a lot less. Okay, and the deal is that it has to do with a specific heat. Water has a very high specific heat. So when we put the metal samples in there, hundreds of degrees, But when we put them into the water, it only made the temperature go up to about 92, 93 degrees, about 20 degrees, give or take a little bit. So it made the water go up at 23 degrees. Okay, and even though they had the same amount of thermal heat, thermal energy in them, they did not have the same temperature. It didn't cause the same kind of temperature rise in the water. Why? Because water has a high specific heat, and it's hard to make it heat up. Okay, and so it takes a lot more heat to make the temperature go up. Now that is a good thing for us because our bodies are made mostly of water. If we were made out of metal, we would walk out in the sun, and as soon as the sun started hitting on us, our temperature would shoot way up. Well, it turns out that if our temperature gets more than about 5 degrees, 5, 6, 7, 8 degrees higher or lower than 98.6, we get our bodies start shutting down, proteins don't work, reactions don't happen, and basically we start dying. Okay, and so we fortunately are made mostly of water. So when we go outside, even though the sun hits us, it same amount of heat hitting us, but our temperatures do not go up very much because water does not heat up very quickly. Okay, in the middle of the summer, for example, when it's very hot and dry, the temperature tends to be higher. Why? Because there's not much water in the air. If there's water vapor in the air, it absorbs a lot of the heat without the temperature going up. Okay, so notice you can absorb heat, but it doesn't necessarily increase the temperature if you have a high specific heat like water. And the same thing has to do for cooling down. If we're made out of water, we can lose a lot of heat without our temperature going down very much. Okay, and that's a good thing because that keeps us at that steady temperature all the time. Okay, metal, on the other hand, so if we were made out of metal, it heats up very quickly, but it also cools down very slowly. Take aluminum foil, put it on my grill, and it's hot. Okay, it gets hot real fast. That's all we can cook on it. But if I peel it up a little bit, and let it sit there just for a second, and then I can grab it with my bare hands. Why? Because it loses heat very quickly also. So if you have a low specific heat, basically it's like how much heat can I absorb and how much does it change my temperature when I do that. Okay, and things like water that have a high specific heat can absorb a lot of heat and not increase their temperature very much, or they can lose a lot of heat without decreasing their temperature a lot. Things that have a low specific heat, like metals, there doesn't take much heat to make their temperature go up. They can, if they lose heat very quickly, and they make their temperature go down. Okay, so that's a very important thing, and various things have different specific heats. All right, now since we're here, we're going to also look at another thing. This is, forgot you can't see it. Here we go. All right, let's see everything you need to see. I think. All right, we have a Coke can here, and inside it we have some. Rain just went dead. Okay, there we go. We have water, just a little bit of water. Okay. Now, as it heats up, it changes to a steam or gas. But what do we know about steam and gas? As it gets hot, it spreads out. It gets bigger. It takes up more space. Okay, and it also has a higher pressure inside there. But it spreads out. It doesn't take up. We can probably see maybe some steam. There was steam coming out earlier. Okay, even though it's still got water in there, the steam spreads out and takes a lot of space. So we have all these hot atoms in there that are moving very fast and spreading out really far apart. Okay, now what we're going to do is take it upside down and stick it inside of this. Okay, so here we go. We grab it and we put it upside down, and boom, just like that. Guess what? The easy way to crush a can. All right. So basically, and why can I touch this? Well, because all the heat from the can went into the ice water. Okay, now as it did that, let me get the ice piece off here. Okay, what happened? Well, all that we know, when something gets cold, it contracts. So the air that was in there, okay, got small. All the steam that was covered there probably made like one drop of water. So it went from filling up the whole can to one little drop of water. Well, this was underwater, so we created a vacuum. The only way it could fill up, there's two things. One, when all this air quit pushing on the inside, now you have the air pressure we talked about last time, 15 pounds per square inch, crushing it from the inside. Now the other thing is, since all that gas went to a little tiny space, is water could try to rush up there and take its place. And sure enough, there was some water up inside of it as well, which cooled it down even faster. But there you go, crushed can. Why? Because with the air pressure because that expanded steam in there shrunk into a little water droplet, low pressure, so the air pressure crushed it, and the water tried to take its place. Why? Because when things get cold, they get smaller. Okay, which brings us to thermal contraction and expansion. Let's talk about that a little bit. All right. Um, Gases definitely expand and contract when the temperature changes. Okay, that's not probably too surprising. Sometimes you see balloons in the mornings look kind of like almost deflate. Why? Because cooler temperatures have caused the air inside the balloon to contract and get closer together. Okay, if you heat it up, it would expand. All right, now we know that happens in gases. All right, we just demonstrated that with the can over there, how that when it got cold, it contracted and got small, and therefore allowed the air pressure to crush it. Okay, but what about liquids? We showed last time with syringe, you can't hardly squeeze liquid. Do liquids change size? And the correct answer is yes. They also expand when they get hot, not when they turn steam. Just if the liquid gets hotter, it will expand, but slightly. You can't even notice it usually. Okay. If they get colder, they will take up less space. But once again, if you look at it, you say, oh, that's shorter. Okay. You can't do that. But we can show that. All right. So we're going to get ready to do another experiment here. All right. We're going to get some torch. It's always good to have a propane torch. No day is so good that it can't get better if you put fire into it, right? Okay, exactly. All right, so this is a torch. All right, I think it's pretty straightforward. This is a bimetallic strip. Ooh, fancy name. Well, one side of it is copper, kind of has a coppery show. The other is probably zinc or iron. I'm not, to be honest, sure on this particular one. But if you notice it right now, it curves up, okay? But if I heat it, you will notice that it bends down. I don't know if I can see that where you can see it there, but now it bends down. All right, if I let it cool back off, it will start to tilt back up to the side again. All right, so says, well, how does that work? That's a good question. All right, so basically, metals expand or contract differently or different amounts. Okay, or expand. So when I heated this up, the top metal, okay, which is the zinc, okay, expands more. Well, the only way, put this down here for a second so I don't burn myself. Okay, all right, the only way it can expand is to get bigger. So it gets bigger, but the copper on the bottom does not expand as much, and so it doesn't get as big. All right, so I'm still going to hold this. Hang on, let me get a piece of ice. All right, I haven't switched it or anything. All right, let's put some ice on this. Try to do that without burning myself. Hang on. Okay, we put ice on this. Now it begins to contract. Okay. And it is tilting back up again. Why? Because one metal contracted more than the other. So now the zinc is contracted more and the copper did not shrink as much. Okay. And because the metals have different amounts of shrinking and expanding, then it will cause it to bend in directions. We'll talk more about some applications of that later. But let's look at some more examples of that. All right, here I have a ball. How fancy is that? I know what you're thinking. All right, a ball, metal ball put on this handle. All right, and we have a ring right here. And if I stick these, the ball passes right through it. Okay, now if I heat up the ball, can't hold all this where you can see everything all at once, but you just have to take my word for it. Okay, so I'm going to heat up that ball. Now we know that if we heat up a ball, it should get bigger. So let's see. All right, so we're getting it there pretty hot. All right, now if we try to put that through the same ring we had before, it still works. Well, then we'll just have to keep working at this. Apparently, we haven't expanded it enough. Pretty hot. All right, let's try it again. Ah, now it's so hot it will not fit through. Okay. Now, question is, what if I heat up both of these? If I can turn this where you can see what I'm doing here. Okay, so now we heat up the ring and we heat up the ball. What will happen? Will the based on what we saw before, we would surely the ring would expand, but what about the hole in the middle? Does that mean it expands, or does that mean it shrinks as the metal expands? And would it get narrower in the middle? Good question. Hopefully, just a second, we will have a good answer for that. And the correct answer is if you expand both of them, the ring expands, but that means the hole expands, the outside diameter expands, everything expands, and so it will go through it again. Okay? Then if I were to cool it back down, let me just do that real quick. Nothing there. Nothing there. All right, cool both of them down, and yes, they'll work again. All right, let's still work. Now they go through, both very hot, but they're both hot or they're both cold. Now, if I wanted to say I had a bolt and a nut and bolt, and I wanted them to heat up. Would I want to heat up the screw, the bolt, or would I want to screw the nut that you turn on it? Well, if you screw the nut, if you get the nut hotter, it expands, and that makes it fit even tighter on the bolt, on the nut. So that's not good. But if, on the other hand, you heat both of them up, or ideally, if you get the screw cold so it contracts, pulls away from the bolt, and heat up the nut, sorry, so if you heat up the bolt, it pulls away, it contracts, and if you could heat up the bolt, that would be the best combination because they would separate from each other and have the most room between them and then be the easiest to loosen up. Okay, same thing here. If I got one of these cold, if I got the ball cold and heated this up so it expanded, then that would be the easiest way to get it through because it has a big distance. Now, it expands in all directions. Okay, for example, we have this bolt and we have this one. Okay, notice right now if you go through the holes, okay, and we will notice that, if I get that out, okay, it can fit right between there, right? Okay, but if I heat up the long skinny bolt part, heat up on both sides. All right. If I try to put it through the hole, it won't go anymore. Okay, and if I try to put it between these, it will not fit. So not only it gets bigger around, it also gets longer, it expands in all directions. Now, does it do this a whole lot? No, it's a fairly small amount, but it is a very real amount. Okay, roads do the same thing. If you have black asphalt road, it expands when it's hot, it contracts when it's small. Okay, now usually the road's sitting on top of the earth stays pretty constant temperature, so it doesn't heat up a lot, except for obviously on the top surface. But if you have this an overpass where there's air underneath it and air on top, well, the air gets a lot warmer during the day and gets a lot colder at night. And so the overpasses tend to go back and forth, expand, contract, and it would tear them up and you'd have potholes all over the place all the time. So if you look on a overpass, you will see like a little metal zipper at each end. Or sometimes in the middle, every so often, and that allows it to expand. The teeth go in farther, or they contract and pull back out, and it allows it to do that without buckling the road and making big chunks come out and making potholes. Okay, all right. So that is a very real thing. Now, so expanding and contracting. The hotter they are, they expand. They get colder, they contract. What are some practical uses for that? All right. One practical use of up the thing here. Okay. One of the practical uses is a thermostat of various kinds. Okay. Right here we have a bunch of wires that hook up to these light bulbs here. I'm going to hook up here just so you can see them. Okay. And they hook in here and in here, and they hook over to a 9-volt battery over here. If I put this little piece of metal here, it completes the connection, and you'll notice that the lights light up. All right, but let's say I want them to go off in the daytime when it gets warmer. Now, I don't have a sun I can put in here, so I'm just going to get a little a match. And I heat up this metal, which is actually a bimetallic strip. Well, actually, I don't know if you can see that, but it bends away from it. Okay, as it bends away, there's no connection, the lights go out. So this will make my lights go out during the daytime. Now, as it cools back down, this bimetallic strip will eventually touch back. And when it does that, we will have lights again. Oops. There we go. Sorry, it didn't touch. All right, so we'll have lights again. So basically, when it heats up, it pulls away from it, bends it away, and there. So that's a way to control electrical supplies that way, and that's basically what a thermostat does. Okay, when it gets too hot, it bends and pulls away, breaks a connection. Now, instead of doing it with a straight piece like that, usually you will see some kind of, I don't know if we can focus on that or not. That's too close. But there's a coil wire there in the middle. Okay. And normally, what would happen is as it gets hotter, this wire will coil up here in the back tighter and it will turn the needle this direction. Okay. As it gets cooler, it will uncurl and that would pull the needle back the other direction. So this is just a simple oven thermostat with that little coil of wire in the back. In a old-fashioned thermostat, they have what we call a mercury switch. All right, in a mercury switch, you have a piece of metal that comes out here and one over here, one here and one back here. There's two places here. Now, if it's attached to a coil, well, if the coil, say it's getting colder at night and you want the air, and this turns on the air conditioner, well, it cools up this way. Well, the mercury's down at this end, away from the two pieces of metal, and so it turns it off. Okay, but say it gets hot during the day and it cools back the other direction. Eventually, this little mercury drop, which is metal, will connect those two pieces of metal and it makes a connection. Just like this turned on the light, that will turn on your air conditioner. Okay, and you could have the same sort of thing, just doing the opposite for your heater. Okay, and so these were what we call mercury switches. This one came from a school in Paradise. They had replaced it, but they left it on the wall, and I took it out. Okay, but yeah, that's a mercury switch, and basically it has to do with the same thing. As you have two pieces of metal heating and expanding and contracting at different times, then they'll go back and forth like that and turn it on and off. All right. Now, last thing about expanding. If you ever want to say, "Oh, I'd like to have some mercury," yeah, ooh, there we go. There's some mercury for you. That's probably the biggest amount of mercury you'll ever see in one place. Certainly the most I have ever seen. One of my students brought it in from their parents had a hardware store and they didn't know what to do with it anymore. And so they brought it to me. And I said, thank you. All right. Because I like those kind of things. But basically, mercury is in a thermometer. When it gets hot, it expands. Okay. So you put it in something hot, it expands. Well, if it only has a little thin tube in the middle there, it expands quite a bit. If you look at the tube inside it, I don't think you can probably see that, but you probably couldn't slide one of your hairs. I'd try it, but I don't have any hair. And you probably couldn't even fit your hair in there. How do they make a tube that skinny? I don't know, but they do. And that tube is so small, it doesn't have to expand very much. And the mercury moves up quite a bit up the stem, and therefore you can read the temperature. And that's basically how it works. If it gets colder, it contracts, gets smaller, and goes down the tube. As long as no one shakes it and there's gaps in between the thread of mercury, it works just great. But just for the record, don't go breaking thermometers trying to get the mercury out. Even if it is silver, there's not that much in it. Okay, just a couple drops. It's really not worth it. All right. Okay, so onward. All right. Let's talk about some ways that heat is spread. Okay, heat transfer. Okay, heat goes from one place to another. If heat is when heat moves, or heat we said is when thermal energy moves from one object to another. We know it always goes from the hotter object to the colder object. Okay, so let's talk some about ways that it can transfer. All right. So just to begin with, let's just get some fire because once again, life is always better with fire. All right. So I'm going to turn on the gas. Technically, there we go. All right. Now, let's pretend this was a campfire, which is not, but if it were, okay. All right. If I were to touch it or to put a pan over it, the flame would actually touch the thing. All right, and then I would touch the pan because it would get hot and I would burn myself. Okay, that could happen. All right, that is conduction. Okay, if the flame's actually touching the metal and then I touch the metal handle, which is touching all the other metal, it gets hot because of conduction. So conduction is when things touch, okay, and heat passes by touching. Another way is if I felt up here, I would feel warm air rising. Why? Because, well, warm air expands, takes up less space, it's more space, it's less dense, and because it's less dense, it rises and buoyant. Okay, and it rises. That would be convection. And then eventually over here it would cool down and it would sink back as it cools down, and then it would come back over here and get heated up, and you would have maybe a convection current. Convection is when the fluid, either air or water, heats up and the whole thing actually moves. It's not going to happen if you have a solid, but it is going to happen if you have a fluid, either liquid or gas. Okay? And then the last one is, even if I'm sitting off here to the side, I can feel the heat from that. Why? Because it's radiating, as in rays of heat coming over here and hitting me, okay? And so actually I might be feeling all three of those, okay? 3 types of heat transfers. Now, let's look at some other examples real quick though. All right, say I have a piece of paper. If I stick it in the heat or flame so it touches, it catches on fire pretty quick, right? Doesn't take long, boom. And we better put it out before we make a big mess, right? Okay, but let's try something else. Same paper, same piece of paper actually that came from. All right, and I'm going to put this, all I've done is wrapped it around an aluminum rod, and I'm going to put it in here, and let's see what happens to it. All right, I take it out, and it does burn, but not nearly as much, okay? You can see, I don't know if you can see it up here, there's an edge up here that's not attached to the rod, and it did actually burn and keep burning for a little bit farther. So even though it's hot enough to burn, it doesn't usually burst into flames, except for where the paper is on the edge and it's not actually touching. Now, so why then will it do this? Okay, if I take this out, we have it on there too tight, which is good. All right, there we go. Okay, it has not been burned completely to ash. It's still a nice tube. Okay, and so we say, hey, that's kind of cool. Why? Because the heat is being conducted. This is an aluminum, and it's a very good conductor of heat. Not as good as electricity, although it will conduct electricity, but a very good conductor of heat. And because it carries the heat away from the paper so quickly, it actually doesn't burn. Okay, and so it is conducting the heat away from the paper so quickly that it doesn't really completely burn and turn into ash. Now, someone says, what if we just had a tube of paper like this? Okay, all right, I'll just put it down there. Let's put it in there. It's burning. Okay, sorry. At the top, it's burning completely. Okay, you can see that. Okay, it's catching on fire. So I said, well, what if it comes down and burns my hand? Well, I'm pretty sure it's not going to, and sure enough, it doesn't. Why? Because when it gets down to here, guess what? You can tell by the shape there, there's a metal spring in here. Okay, and so it is noticing where it touches the spring, the paper is not burned as bad. Why? Because it's absorbing the heat so quickly, it does not allow it to completely burn like it did up here at the top, where it's just completely mushy little ashes. Okay, and so, yeah, that's kind of an interesting thing. All right, but once again, that's conduction because it's conducting the heat away from the paper so quickly that it doesn't have time to completely burn. Okay, you can do a similar thing if you have a paper or plastic cup and put it in a fire with water in it. It will not burn because the water absorbs the heat so quickly, it absorbs so much heat that if it's in the middle of the fire, the top part of the paper cup will burn, but then the part that still has water will stay there. In fact, you can actually sometimes boil water in a paper cup, but as it boils away, the top keeps getting burned a little more and more because it has to be water there to absorb the heat away from it. Okay, but that's kind of by conduction. All right. Let's see. What else would we like to do? Let's do an example of convection, but let me go move and then we'll come back. All right. Before we get to convection, there's one more thing we need to do with conduction. Sorry, but this is one really cool. I like it. All right. You see those two, I guess? Yeah. Okay. These are two black blocks. Now this one, you can hear, is fairly metallic. If you feel it, it feels heavy and cold. Okay. And over here is a plastic one. If you feel that one, now the question is, these little rings are just here to catch the water, so I don't have to clean up as big a mess. It'll probably still make a pretty good mess. But the question is, if I put a ice cube on each of these, which one will melt fastest? Will it melt on the cold metal or the warm plastic? Okay, the one that felt warm to the touch. And if you're looking very closely, you can probably already tell the answer to this one. Okay, bye bye. This one's almost about half melted. This one is still pretty much about like it was before. There's a little bit of water that was in a glass of water, but you can see this one's going fast, fast, fast. So it turns out that it's losing on the metal one. Now that usually confuses people because well, it felt cold. Wouldn't it be the one that felt warm? Well, think about it this way. What's warm? Your hands. So if you hold this one and you feel the warmth, that means the warmth is staying in your hands because cold is the absence of heat. So if you felt it warm, that means the heat is not leaving your hands and your hands still feel warm. But when you feel the metal one, it feels cold. What does that mean? That means all the heat is conducting out of your hands, and that's why it feels cold. So it's actually a very good conductor. It's a metal, it's a very good conductor. Plastics in general are not very good conductors of heat, and so the heat is not being conducted into the um, ice cube very well. And yet you can see that the metal one has almost completely melted because it's so good at conducting heat in it conducts it right up into that ice and melts it very quickly. Now, because it's conducting the heat, it feels very, very cold. Okay, it's conducting the heat not only from my hand, but also from the air and whatever into that ice cube. And so it melts very, very quickly. All right, now on to convection. For this one, we have a special convection tube like this, like so. Oh, I forgot something. Hang on, I'll be right back. That's better. We have some fire. We need fire. Never can do much without fire, right? Sit over here where we don't burn anything. All right, going back to the convection tube. It's just a glass tube with a little end on it so we can put water in it. I have some dye down here in this bottom corner, so hopefully we can see how the water is moving inside of it. Let me get some water in here. No, maybe not. All right. Now we have the dye. Hopefully the darkest dye is over here in the corner. But we are going to heat up the dye. And hopefully you can see how it travels around. I'm going to get real close because I don't want to break the glass. But you can see as it's climbing up here by my hand as it's going up. Okay, so it's rising, still going up. Okay, up to the top corner up there. And then it's coming back down. Okay. I turn it that way, it'll even, you can see how it's definitely rising and then coming, and you can see it coming down this far side over here. Okay? All right, and so that's convection. It's just going to go in that circle over and over and over. Okay, convection is where the fluid has to be a fluid, something that can flow. The actual fluid moves, and so when I was heating this, you could see the water and the dye with it was going up this side and working its way around and back over here. Now it's pretty much the solid all the way around, so you can't really tell as much, but that's basically what we're trying to look at here. Okay, so basically it is a convection. It's when whatever the fluid is, the water, liquid, or gas, same thing happens in air, this is what causes wind. The sun heats up the air, it gets less dense, it rises, it cools off, it sinks, it comes back down over here, it heats back up when it touches the ground, okay? And so you have this circle, and if you're on the ground, on the bottom part of that circle where the wind is going across the surface, then you feel that as wind, okay? And we talk about the direction of the wind, all right? But that's caused by convection. So when the fluid, either air or liquid, actually heats up and the actual air or liquid moves around. Same thing happens in a boiling pot of water. If you look all around the edges, there are going to be little billows around the edges where it's circling around and around, heating up, cooling off, coming back down, okay, and so forth. So that's convection. It's where the liquid or the air, the fluid, actually moves around. All right. So for our last and grand finale here, we're going to look at this. This is basically a Florence flask, which is going to put down light bulb, but has water in it a little bit at the bottom. It has a test stopper in it with two things of tubing coming out, so that if I were to heat this with a solid stopper in it, the gases and everything in here would expand and it would go shooting off and hurt somebody. So we have to have those glass tubes coming out so that hopefully that doesn't happen. All right. Now we're going to try to heat up the water here, okay, and get it to be bubbly good and everything like that. We want it to evaporate. Okay, let's again. That's what we have to have because things, when they get hotter, expand, especially if it turns to steam. Then there's going to be shooting out steam and stuff out here. But if you had a stopper on there, then it would just build up a lot of pressure and blow up the whole thing, and that's not a good thing. Now, over here, we have an apple. Well, actually, it's a jelly jar. It looks like an apple. All right. I don't know if you can see that very good. I may have to change something here. Let me get a white thing so you can see that a little bit better. I'm colorblind, so that may be why it doesn't show up very good to me, and maybe it shows up just great to everybody else, but we'll see. Anyhow, now we have a white thing on there. All right, so this is has just red water in it, because the apple needs to be red, right? So whether you're bobbing for it or doing whatever, it's got to be whatever. So, all right, we're going to heat this up. It's going to take a while, but it's going to create steam, okay, just like kind of we did in the can before. And we're going to turn it upside down inside the red water, put the two tubes down inside the water, and just see what happens. Maybe nothing, but that's the fun of excitement, not the magic show where it works every time. But sometimes Mr. McMurray doesn't get to prep his experiments, so who knows? Maybe nothing will happen. Maybe so. All right, I'm starting to get a little heat in there, a little bubbles starting to bubbling up. Some of it's turning to steam. Some of it is condensing on the inside of the neck, if there you can see that. I don't know if you can see that very good or not, but it may be. Oh, whoops. I suffocated my flame. Hang on. There we go. All right, so it's starting to steam up in there pretty good. Starting to see water condensing, a lot of steam coming out here, shooting out. All right, that'd be kind of like a convection current. All right, it's getting pretty good, but we'll let it go a little bit longer just to make sure we've got a good heat going on there. And then we'll see what happens when we flip it upside down. All right, I think that's good. We're going to turn it upside down and wait for nothing to happen, apparently. I don't know. Let's see. Maybe it messed up. Oh, there we go. And that's the easy way to get the water uphill into the flask. All right. Now, question is, can I grab this? Well, that we know this was very hot just a minute ago, but it also had room temperature water in it, and so yes, I can grab it. It may be a little bit warm, but it's fine. Why? Because heat is the transfer of thermal energy, and all the heat that was in this transferred into the cooler liquid that went inside. But there you go. All right. So this is very similar to what we did with the Coke can, except that this time it was sealed more, and you had the air pressure could not crush the glass. So even same kind of thing happened. We heated up. We had steam inside of here. Much atoms spread far apart. When we turned them upside down in this, they began to cool off as heat went into the room. It cooled off the liquid. As it did that, it began to condense, which made a vacuum. But this time, the air pressure couldn't crush it because it's glass, not a thin aluminum can. And so the only way it can relieve that pressure was to suck up the water. We had a vacuum, and it basically had a pressure differential, okay, not really suction, but a pressure differential, low pressure in here, higher pressure outside, and the air pressure from outside pushed the water up into the flask, okay? And so then as the water started splashing in here, it cooled it off even faster, and that just made it happen faster. It's a little slow at first because it takes a little while for it to cool down enough to make a difference. But once it does start cooling and then it starts contracting, then it starts sucking the water in, And there you go. It's all full up. All right. Good news is there are no tests this week. However, I believe this is the week for the article summary on the 25th of October, at least the week I year I made this. So make sure you get that article summary done. Questions due on Saturday, and quiz will be next week. All right. Have